Hello, so this is the one and only video for section 6.6. So this video, we're going to look at the applications of what we did last section to finding regression lines. So this should be somewhat similar to if you've taken a stats class when you're given a set of data points and you want to find a least squares line or a regression line. This should be similar to that. So the problem that we're given that we want to apply our linear algebra to, we're given this set of n data points, and we want to construct a linear function. So linear meaning that the highest degree x term in this function is equal to 1, which could predict new y values given an x value. Now, if you've ever looked at a set of real data, of course, the real data almost never strictly obeys a nice linear function. And so generally what we have to do is come up with a function, again, that even given the data we have, tries to predict the y values given the x values, right? So you might get a picture that looks like this, right? Where the data points are these dots here, and then the regression line is this line going through that, you know, almost looks like a line going through the points, but isn't quite a line going through the points. So I just wanted to quickly introduce a few definitions here that we will talk about. So after constructing this function y equals beta 0 plus beta 1x, which we'll talk how to construct this function in a second, each point x sub I and y sub I, we call y sub I the observed value. So in this way, the y sub I is the actual measured value that we would observe. And b sub 0 plus b sub I times x sub I is the predicted value, right? So maybe you're trying to predict, say, traffic in a busy city given the time of day. The actual amount of traffic would be the value of y sub I, and the amount of traffic you predicted there to be at the given time would be the predicted value. And so then a residual is just the observed difference between the observed and the predicted value. So it would be equal to y sub I minus beta naught plus beta 1 x sub I. So it would just be basically the difference, and pictorially it would just be the length of these dashed lines I've drawn. So the amount of distance from the predicted value to the point, the corresponding x value on the line. So generally, how we want to calculate this function y equals beta naught plus beta 1 times x is the following. So generally we want the line the regression line y equals that minimizes the sum of the squares of the residuals. We want the line that minimizes the sum of the squares of the residuals. So that is, we want to minimize y1 minus beta 0 plus beta 1 x1 quantity squared plus all the way out to y sub n minus beta naught plus beta 1 xn quantity squared. So I'm not 100% sure the reason this sort of standard was chosen. My guess would be, so if you notice that, like, just trying to minimize the sums of these lines would be sort of difficult, right? Because certainly some of the, if you calculate some of these differences, right, sometimes the difference is going to be negative, sometimes it's going to be positive. And so you might say, well, maybe you could minimize the sums of the absolute values of the differences, and that might make sense. But it turns out if you do it this way, as we'll see in a second, we have a really nice way to do it using linear algebra if we're going to minimize the sums of the squares. And so the line that does this is called the least squares line. It's also sometimes referred to as a regression line. So, how can we use linear algebra to find a regression line? So first, I want to convince you that if we're given the data points x1, y1, all the way up through xn, yn, and sort of a shell of a function, y equals beta naught plus beta 1. So basically, we know we want our function to look like this, but we need to solve for the constants beta naught and beta 1. I want to convince you that we secretly have a matrix equation here that ideally we could solve perfectly, but as we'll see, we won't be able to solve perfectly. So how do we have a matrix equation? Well, we're going to let X be a matrix. So this is capital X here, whose first column is just an entire column of ones, and whose second column consists of all of these X values. Now remember, these X values correspond to the known data points we currently have. So these aren't variables. These are known measured data points. We're going to let B be the following vector, beta naught, beta 1. Where here, beta naught and beta 1 are two variables that we want to solve for. Note your book uses beta here as the vector. I'm using B in part because it was easier to type it up using B and making sure that it was clear that it was a vector. So I'll make clear that it is a vector there. So this is vector B, matrix X, vector B. And then we're going to let Y be the vector containing all of the Y values. So notice we want a least squares solution to X times B is equal to Y. And to see this, let's look at the first row of X times B equals Y. Well, what's going on in the first row? So if we do my matrix vector multiplication dance, I'm going to match up 1, x1 with beta naught, beta 1. And that should equal the first row on the right-hand side, which is y1. And so notice, this is the equation that in a perfect world we would be able to satisfy with our function. But remember, the whole point is we're not going to have an exact function, so we need to come up with a least squares solution. That is, we want a vector B that gets X times B as close to the vector Y as possible. So the one thing I haven't shown you yet is that, in fact, the least squares solution that we get solving a matrix equation actually coincides with our goal up here of finding the line which minimizes the sum of these squares. But remember, what a least squares solution does in terms of a matrix equation is it minimizes the value of, well, the difference of the vector y minus the vector x times b. But notice that this is just equal to the square root of the sums of the differences of the entries, which, as it turns out, is exactly the thing we're trying to minimize. So in fact, the least square solution we're finding with our matrix equations perfectly coincides with the idea of a least square solution the way we defined it here, because exactly what a least square solution to this matrix equation is doing is minimizing the value of this. And the square root doesn't matter because the square root function is an increasing function. So if I minimize the square root of this, then I've also minimized this. And that's exactly what we wanted to do. So it turns out that finding a regression line just amounts to finding a least square solution to this matrix equation. We're going to look at an example now of doing this. I always love, learning math when, because I think I had taken statistics before I had seen something like this. And I remember in my stats class, we might have mentioned kind of, okay, what is the regression line aiming to do? But I don't remember learning like the definitive way you can actually find the regression line that is actually doing it. And it's just so cool because it's going to turn out finding this regression line is like a few simple matrix multiplications and then solving a matrix equation, and it's like you're done. Like, wow. So let's look at an example. So we want to find the least squares line corresponding to the data points, corresponding to the data points 1, 0, 2, 1, 4, 2, and 5, 3. So what we just saw is we want a least squares solution to the matrix equation x times b is equal to y, where we define our matrix vector as follows. X, remember, is a matrix with a column first of 4 ones, then a column containing all of the x entries in order. The matrix B here is our variable matrix containing variables beta naught and beta 1. Right, we want to solve for the values of these that give us our least squares line. And y is the vector of length 4 containing all of the y entries. And so now we've seen in last chapter, probably the way to do this is actually to solve x transpose x times b is equal to x transpose times y. So what we need to do is first calculate x transpose times x. For 1 plus 2 is 3 plus 4, so that's 12. 12, and we get 1 plus 4 is 5. 16 is 21, should be 46. Yep. So this is X transpose X. Next, X transpose Y. It's 1, 1, 1, 1, 1, 2, 4, 5 times 0, 1, 2, 3. I like how your book chose that vector. So I pulled this example out of the book, and I think the vector I've used the most is the vector 1, 2, 3, or some iteration of that vector. And so then X transpose times Y, you should get 6 times 25. And so this means we want to solve matrix equation 4, 12, 12, 46 times beta naught, beta 1 is equal to the vector 6 times 25. And row reducing the augmented matrix and solving, you should get beta naught is equal to negative 3/5. Beta 1 is equal to 7/10. And so this means that our least squares solution, or our least squares equation, is y equals negative 3/5 plus 7/10 x. Is our least squares line given this set of data. And so as you can see, finding this least squares line was just a few matrix operations, or just required a few matrix operations. But it gets even cooler than that, because notice here, solving this matrix equation really didn't depend on the form this function took on. And what I mean by that is that, like, I can always add constants to this vector and add columns to X, right? And so this then means that this method of solution isn't actually restricted to just linear regression. So suppose we have, again, say, the following data points: x1, y1, up through xn, yn. And let's say we wanted our regression model to have the following form. So let's say instead of a linear model, we wanted a quadratic model. That is y equals beta naught plus beta 1 times x plus beta 2 times x squared. So notice again, I just want to solve for beta naught, beta 1, and beta 2. And so this is equivalent to finding a least squares solution again, given sort of the assumption that our goal is to minimize the sum of the squares of the residuals, to x be equals y, where this time for x, well, my first column is going to be all ones again. My second column is going to be the linear term. And my last column will be all of the x entries squared. Then b will be a vector of length 3, beta naught, beta 1, beta 2. And y will be y1 up through yn. And so notice to check this, right? Because the constants we're solving for themselves are not sort of quadratic or squared in this way, right? The matrix equations don't really care what functions of x I have here, right? As long as I enter them in columns in order, right? So the first row now of xb equals y, well, again, doing my matrix multiplication dance, I would get beta naught plus beta 1 x1 plus beta 2 x squared, x1 squared, is equal to y1. But remember, we're just trying to predict y1 given this function of x1, right? Given x1 squared times beta 2 plus x1 times beta 1 plus beta naught. So in fact, because this method of solution doesn't care how many columns or how long this vector is, as long as I've got more variables, as long as I've got, you know, at least as many rows as I do columns, we can actually do this with any model that we want. So I think my favorite one, so certainly we could do it with a quadratic model like this. Your book actually has an example that I think is really awesome. You could even do it with a model like beta naught cosine of x plus beta 1 sine of x, right? And all you have to do is just update your x and your beta matrix, right? So now our x matrix would be a matrix with 2 columns, cosine x1, cosine x2, cosine xn. And remember, these are all just numbers since the x values are, you know, hard data points that we have. And beta naught would be, or sorry, the b vector would just be this again, and y would be y. And then again, it's just a least square solution to x times b equals y. And so we can actually try to model y with any function of x I have here and find the least square solution using this method. Again, just by setting up the correct matrix whose values are the values that I would see given each individual x point corresponding to the rows. And then it's just finding a least square solution. So like I said, I thought that was really cool when I first saw it. But anyways, that actually will wrap up chapter 6. So next week we will do chapter 7. We've got 3 sections in chapter 7 that I want to cover, and then we'll take our final.